In the earlier demonstration, we developed an algorithm for Lagrange polynomial calculation, and it was programmed in Colab Python. So this was the algorithm. One modality of Lagrange polynomials is that they can be used to compute and the inverse interpolation, which is like if a value of y is given, then we can use the value, we can calculate an estimated value of x. So for example, if we have these 5 data points, so Lagrange polynomial can give us the estimations based upon a 4th degree polynomial. For example, if I define the data set from x as log of xs, so I can compute for some values of x which are from the range from 0 to 6.5, which was defined earlier. Yes, so from 0 to 6, and there are about 50 points between 0 and 6, so there are 49 divisions. So let's extend that one and define it again here. So this is the x. Let's define it for from 0 to for example 8, and let's choose 50 points. So we have got Lagrange estimates of corresponding y for x, and if we plot these values, so we have these interpolated values where for every x value a value of y has been generated. But a problem is that at what value of x we have some specific value of y, or for example the root which is the point where y value is 0. So this can be accomplished by constructing the polynomial in other way around, like x as a function of y. Generally we compute y as a function of x. So here with the same data xs and ys, and the same function can be used. For example, I write Lagrange function and I define the data set as ys xs, and I can give the value of y for which I requires a value of x. So for this problem, it generates an estimate of x as 1. So we can find that this is the x value 1, and it is close somewhere for the value of y. This is not going to be exactly equal, because when the polynomial is constructed x as a function of y of 4th order, it is going to be something very different. So if I show this one, so this will be, I will choose a domain of y values, say from -1 to 2. So I define yt's as, for example, numpy linear space -1 to 2. Okay, from -1 to 2, and I take, say, again some 50 points, and I generate some corresponding x values with the function Lagrange with the same data y as xs, x as a function of y for all values of y of t. So I got the values of xt, and now let's plot again the data. Plot xs ys as red circles, and I plot the function which was earlier plotted, y as a function of x, and which was with the data x and y. So this was for the forward modeling, y as a function of x. So I plot it as a blue line. And the third thing, I'm going to plot the third function, which was computed as x as a function of y. So I'm going to give the values xt, yt, and I plot it here as a green line. Now plt plot, plt x label. So we have x, and plt y label y, and this now I'm going to plot here three different data sets. So there must be legends. So I write legend, and in this case I have to write the first one is the data set, the second one is y, the function of x, and the third one is x is a function of y. So we have got three data sets. So let's plot it. So we can notice the differences. The green line was computed, green curve was computed as y as a function, well, green was computed as x as a function of y, so which was xt and yt data, and the blue was computed as the x as a function of y as a function of x, so the forward modeling, and we can see the green curve as the inverse interpolated data. So that's the modality of Lagrange polynomials, that we can compute the interpolations in inverse fashion.